let's talk about like some of the practical aspects when you train your neural networks. So we'll talk about like different concepts which you should be aware of. So as we discussed, like you will use a stochastic gradient descent, and what's going to happen is, since you're training on like a mini batch, so whatever decision you make, like, or whatever updates you have taken, like using those samples, it might not lead to like a local minima, right? It might not always reduce the loss function, because that decision was not based on all the samples, right? It was based on only those few samples. So it might go in any direction. So when you actually train your network and you try to plot your loss values, so let me try to explain this curve over here, and you'll have to do this a lot when you train your networks. The x-axis is the iteration, okay, starting from zero when you initialize your network. As you move towards the right, it's showing you like iterations, and if it's like 500 iterations per epoch, then at 500 it's like your one epoch, right? But that's fine. We will use like both the terms to plot this. You can use epochs as well. You can use iterations as well. Iterations is actually better because that gives you like fine-grained visualization. So that's x-axis. Y-axis is the loss value. Okay, so what's your loss? And we want to minimize the loss. And as you initialize randomly, you will have like a very high amount of loss at the beginning. So ignore like this negative sign. It's just like the loss value you have, and you can have different loss functions, right? So the values will depend on that. So you will start with a very high loss, and as you move towards the right, you train your network, your loss value should reduce. That's what you're aiming for, right? That's how you are taking like those mini steps for each parameter. So your loss should ideally go down. But as I said, you're not training your network like on all the images at once. You are taking like a mini batch at once. So it could be your loss is actually not always going down if you try to validate that on the testing samples or the validation samples. So you will see something like this. So this is like more realistic. You can see it's going down, then again going up. Okay, so it will have like some kind of stochasticity there, but eventually you can look at the overall trend. It's actually reducing. Okay, and then it's kind of a stable here. So this is like a very natural looking loss curve, which you will have to analyze when you train your neural networks. Okay, but still I think it will converge over time. That's what I said. So if you try to visualize this, the same thing in like a 2D space, and this is your local minima, and this you can treat as like, it's not visible like in the flat surface, but think of this as like a bowl. Okay, a curve in 2-dimension. Now if you think about that, like this is like a high point when your loss is high, and as you're moving towards the center, you're actually going down. Now if this is your starting point, your end goal is to reach this point, and of course the best way will be you just jump there, which is actually not possible. And that's why what we do is we take like these tiny steps, and each of this step is actually going in that direction. Okay, so how big these steps will be, that will be controlled by the learning rate. If the learning rate is too high, you will make like bigger steps. If your learning rate is very small, you will take like very small steps. Okay, and both are not good. So you need like a ideal learning rate so that you do reach that minimum point and you reach on time. Okay, so ideally what happens is it will be like a zigzag. It won't be like the straight direction. You might go in different directions, but eventually you will reach this point. Okay, so what we can do is, this is another term which you should be familiar with. This is called momentum. And if you think about this, momentum is actually taking into account what was the direction in the previous step. Okay, it's not just looking at the current step, also the previous step. And that is helping because the previous step will tell you, okay, where it was going in the previous step, then you know the current direction. So you will take both into account to make decision for this step. So it's called momentum because you are considering the past. And if you will keep doing that, then eventually when you're making a decision at any point of time, you're actually considering the information from all the previous steps, right? Because in the previous step, you consider the previous, and in the previous, so it's a chain. Okay, so that helps because in that sense, it won't be like a zigzag. It will be like a smooth transition as you go from this point to this point. Okay, so it's kind of, so this is like your normal gradient step when you are not using momentum. This is your current, this is your updated value for weight. This is the weight value in the previous step. This is the learning rate, and that's the gradient. Okay. In momentum, what you will do is you will have like additional parameter, let's say alpha, which tells you like how much of the information you should use from the previous step. Okay, so this partial derivative, you can see like this is partial derivative or the direction from the previous step. This is t minus 1 here, and you weight that with alpha. And then again, this is the derivative, same thing for the current location, right? So then you will make this step. So this is called using momentum. And of course, like these days, we have a lot of variations of this, how you can use momentum. This is just a vanilla version of that. So this is just to give you a flavor of like how, what momentum means when you are trying to do learning using gradient descent. Okay, so now let's try to understand how this learning rate will affect like how fast your network will converge or whether it will converge or not. So if you use like a very small learning rate, then what's going to happen is if you look at this equation, you will take very, very small steps, right? It will control like the gradient value. So then it's going to go very slow, like in very, very small steps. So it will take a lot of time. So if you increase the learning rate, so this is a curve showing like how it will affect, right? So these steps like is going to be controlled by this learning rate. Now, if you increase your learning rate, then what may happen, you might overshoot like your minima, right? If let's say you're using, if starting from this point to this point, it's let's say 10 units. If you use a learning rate of 20, then this is going to jump like from this location to this location, right? And then again, it will go away. So if you use like a very high learning rate, and again, this is showing the loss curve, which we discussed in the previous slide. X-axis is like the iteration or epoch as you're training your network. Y-axis is showing the loss value. Let's say this is the starting point, which was a random initialization. And these are showing like different variations of how your training loss will look like, or how your network will converge if you train using gradient descent. Okay. So the yellow curve, if you look at this kind of curve you will see when your learning rate is too high. Okay, so what's happening here is you're starting from this point and it's actually going close, but it will just cross this value. It won't go to this point because the learning rate is too high. And it will just keep jumping and eventually it will go out. So your loss is actually increasing. Okay, because it will rise like this level after some time. Then let's look at the other extreme, which is low learning rate. In this case, it will move very slowly, but eventually it will come to this point, right? So you can see like this is like the loss is reducing very gradually, but eventually it's going in that direction. Okay, so the other is the green one. And again, this is kind of a high learning rate because what's happening here is it converges pretty fast, but then stays there. It's not moving at all. And the idea is, let's say you start from this location, you come to this point, then let's say you come to this point, then you just keep jumping here. So your loss is actually never going down because the learning rate is too high. It doesn't know how to take smaller steps. It will just keep jumping here. And that's the stagnant point here. Okay. And red is something which is like the optimal learning rate. It's increasing fast and then it's actually converging to a point. And again, these are all hypothetical scenarios. In real training, you will see like curves which I showed you in the previous slide, right? That's like more realistic, but this is a general trend which you should look for. Okay, so that was about learning curve. That will be useful for you when you train your networks. And as we discussed earlier, you have like certain set of hyperparameters in your network, and one of them is learning rate, which is very, very important. So by visualizing or analyzing those loss curves, it tells you like whether your learning rate is correct or not, and that helps you set that hyperparameter to some extent. Now let's move on to the problem of fitting. Okay? So fitting is something, your network has some set of parameters, right? So essentially what's happening, it's a function, right? And when you're saying that your input is an image and you're making some predictions, so basically you're trying to learn some function which is performing this transformation from image domain to prediction domain. So essentially it's a function, and that function is something which you are going to learn when you are training your network. Now, fitting is something, when you take your data, so those parameters will make the transformations, right? So a perfect fit is something when you have those weight values which takes those input and make a perfect prediction without any error. Okay. Now, if you have too many parameters, then it will be very easy for your network to actually make those predictions, and that's called overfitting. I will describe that in more detail to make it more clear. So the idea is, if you have too many parameters, it will be easy for you to learn that function. You can easily approximate that, right? And that scenario is overfitting. That's not a good idea to do that. We'll talk about that why. The other extreme is you don't have enough parameters. For example, if you just use one neuron to approximate a very complex function, that's not possible, right? One neuron doesn't have that amount of capability. So in that case, it's called underfitting. It means that you are not able to approximate your function well. Now let's try to visualize like how these overfitting and underfitting looks like. So the other point is, if you use a lot of data, because your gradient steps or that learning process being performed on a lot of samples, which will have a lot of variations, so that actually helps you to avoid this overfitting scenario, even if you're using a lot of parameters. And that's one of the reasons why you need a lot of samples to train your networks, because if you don't do that, your network will easily overfit. Okay, so let's first look at the loss curve and how we can relate like this loss curve with this overfitting problem. Now, again, this is the same loss curve. X-axis is like the training iterations or a number of epochs. This is just showing the loss value. That's the starting point. Now, the blue plot is the loss coming from the training samples. So the samples which are using to actually update your weights. All right. And then we talked about, you had like two other splits. One is called validation and the other is called testing. Testing is something which you never look at. So testing, you just evaluate your model. Okay. But validation is something which you can actually peek through. You can test your model in validation and make corrections to your model. So what you will do is, as you are training your model, you will keep computing loss for the validation as well as the test set. Right? And this loss is actually computed over all the samples in the validation and all the samples in the test. So you can see initially all of three are like the loss is very high, which means the network is bad. But if you keep updating the network weights, you can see like the training loss is actually reducing, which should happen because you're using this loss to actually update those parameters, right? And you're moving in that direction, which will reduce the loss value. So ideally, your training loss should always go down unless your hyperparameters are not correct. Now, if you look carefully at these two curves, which are coming from validation and testing, you can see like until some point, they're actually following the same trend, which is reasonable because all the images or all the samples from validation and testing were never seen by this model. Okay, so it should be almost similar for both the sets. And at some point, you can see like the loss is actually increasing. Okay, and you know that like the best model is something like where your loss is minimal. And again, that's questionable. There are variations to that as well. But let's just assume for now that, okay, the lower the loss, the best the model is. So at this point, you can see if you keep training your model, the training loss is further going down, but your testing and your validation loss is actually increasing, which means your model is actually beginning to perform worse on your testing samples, which is not good because eventually you want to test a model on unseen samples, right? So this scenario is not good. And one way to interpret this is, after this point onwards, the network is actually just trying to overfit on the training samples. It's just trying to learn those samples, or it's just trying to minimize the loss value specifically for those samples. So it's not like a generalized learning, because that learning is not being generalized to the testing samples. The loss is increasing there. So usually what we do is, if we see such a point, we say that, okay, this is a point which is like the best network, and you use those weights as model prediction, even though your training loss is actually going down. So we don't care too much about the training loss. We care about the testing and validation loss. Okay, so this is the point when your network starts to overfit. And to avoid this overfitting, we have like different regularization techniques to use. So if you think about, just go back to neural networks and try to understand what this overfitting is. So neural networks, you have the input, you have the weights, you have those edges, right? And those weights are being used to actually transform the input values. Now, if some of your weights are actually too high, if they have very large value, then since the output is nothing but a linear combination using those weights, if one of the weight is too high, then that weight is actually dominating the output. It will control what the output is going to be. Okay. For example, let's say you have 3 different weights, and those weights have value 100, 1, and 1. And then you take the input, you take the linear combination, and let's say your input was again a 3-dimensional vector, which is again has value 1, 1, and 1. So if you take the linear combination, you can see that your output is going to be 102. Now, in whatever way you're going to use that activation 102 in the future layers, you can see that that 102 is controlled by the weight which has value 100. And most likely the other 2 weights are, they don't care, right? So if it's 102, it's 101, or almost similar, right? So that's like one way, like when how your network overfits, it tries to learn those kind of weights which controls the predictions. So to avoid that, what we can do is we can add regularization, and a simple regularization is you try to minimize the values of your weights. You don't allow your values to be like some random numbers. Okay. So before going to like the regularization technique, let's try to first visualize what this data fitting problem is by looking at very, very simple examples. But again, whatever we are discussing, these are simple functions, but you can easily generalize these to complex functions such as neural networks. Now, these dots are your training samples. Okay, so in this case, the training data is just like 2-dimensional coordinates. Okay, so this is the training sample. Now, we want to learn a function which can make predictions about these points. Okay, so as a human being, it's easy for me. I mean, I can see that it seems like it could be like it could be a straight line, right, going from this direction to this direction. And the function which we learn could be a straight line, right, or something like this, or it could be a complex function, something like this, which is trying to go through each and every training sample. Right, so these are 2 different functions which, let's say, were learned. Now, if you try to compare the number of parameters in these functions, and again, that relates to like the number of parameters you have in your neural networks. In this case, it's just first order polynomial. Okay, so you don't need like, you need just 2 values. You need the slope of this curve and the intercept. So it's like 2 parameters to define this function. You can say this neural network, if it is a neural network. In this case, it's like a 9th order polynomial. So you need like that many parameters, right? That will be a very complex equation. But whatever that equation is, it's actually pretty good because it's going through each of these training points. Now, if you try to compute loss of this learned functions, in this case, definitely the loss is not going to be 0, because this is the ground truth. But if you look the network's prediction, it's saying something like this. So there is some difference, right? The small difference between what the ground truth is and what your function learns. And that's true for like most of these points. And they're close to the line, but not completely over the line. So the loss will have some small amount of value. All right. But if you look at this function, which was again learned, a lot of parameters, and it's going through each point, the loss is going to be perfectly 0. because this curve is actually able to predict each of these training samples pretty accurately. All of these points are lying on this curve. Okay, so this scenario is called overfitting. That's what happens if you pay attention to each and every sample of your training data. And if you have enough, like if you have sufficient amount of parameters, you will be able to do that. So this is called overfitting, and this is, I will say, kind of a perfect fit. This is something what we want. So, okay, so this is like, let's try to understand that from a binary classification point of view. So in this binary classification, we have two different classes, red and blue, all right? And all these dots are actually your training samples, again, shown on two-dimensional space. And these curves here are the functions which you're trying to learn. So in this case, this is underfitting, this is overfitting, and this is just like about right on a perfect fitting. Not a perfect fitting, but it's a good fitting. That's what we want. Now, if you try to analyze this, this is a straight line again, very few parameters, 1 or 2 parameters, right? So you have, it doesn't have the capability to learn like this complex boundary, because what we want is, we want a function which can divide like the red samples from the blue samples. Okay, so it will be curved like this, something like this. So this curve will have slightly more parameters than the straight line. Now, this is something overfitting because what it's trying to do is, it's trying to satisfy the loss function for each and every sample in your training data. It's making no mistake. So for training set, the loss is completely zero, because all the red points are above this curve and all the blue points are below this curve. So loss is perfectly zero. In this case, again, you will have some loss. In this case, you will have a huge amount of loss because you are making errors for a lot of the samples. Red are like below the curve, right? And some blue are on top of this curve. In this case, again, it's not perfect because you can see like some blue dots on top and some red dots on the bottom, right? But if you think about, if you were given like some testing samples, okay, so this kind of function or this kind of curve will actually give you a more reasonable result as compared to this plot, which is overfitting, or this plot, which is kind of underfitting. Okay, so let's try to understand. So this is pretty clear. I mean, it's not working, right? Even for these samples, it's actually failing. So if it's not working for training sample, it's not going to work for testing sample. So let's go through the third one, which is overfitting, because it's working so perfectly on training sample. Now, let's say if you have a red dot, which is at this location, right where my laser pointer is. So it seems like it's coming from the red distribution, right? Because it's close to all of those. But this kind of curve will say, okay, no, it's a blue dot, and the method will fail. So that's why it's not good, because it's trying to, like, you can say, please each and every training samples, which is not good. In this case, you can clearly see the distribution. If you pick any red point like on top of this curve, it's going to be red. And if you pick any point towards the blue, it's going to be blue. The challenging cases will be like the boundary cases, but which is fine. That's like challenging even for humans. Okay, so that's what underfitting and overfitting means. And you should also be now able to understand like how number of parameters actually relates to underfitting and overfitting. Okay, so one easy solution for this is early stopping, which we discussed earlier. You just monitor your loss curve. And if your network is diverging, like for your training samples, so diverging is something when your loss started to like increase. That's called the divergence point. So you can use early stopping, just stop there and use that model. You can use regularization, which means like you try to minimize the weight values. Even in this case, when you will have some weights pretty high, right? That's why you're able to form these like complex curves here. So you try to minimize those weights. That's one way. You can use dropout. We will briefly talk about that. And there are many other ways to avoid these problems. Okay, so we won't cover like all of those. So early stopping, we discussed whenever your network is diverging, the validation loss is increasing, you stop there. So that's called early stopping. Now, regularization is something where you try to penalize your network. So this is kind of an additional loss term you add. And what you want is you want to have small values for these weights. So what you can do is you can define like a very simple loss term, which is also called like a regularization term, which will ensure like your values for the weights is actually very small. So again, this is showing a simple example. So blue curve is overfitting, green is underfitting. And you can see that this, if this is a testing sample, the blue one is completely failing, but the green one is doing good job. Okay, so what we do is, if this is your standard loss function, which is taking data as input, these are network weights, and this function is like the network, which will give you some prediction. You will compare that prediction with the ground truth, and that's like your loss value. And this is your regularization term. You have a parameter here, which controls like how much importance you want to give to this regularization. Okay, again, this is a hyperparameter, and you use like the weights of your network as input. Okay, and this is also called a weight decay. And there are different variations of like of this regularization function you can use. You can use L1 norm, which is nothing but you compute L1 norm for each of your weights in the network. Just take the positive absolute value of that, and you just minimize that. So it will make sure that you don't have high values for weight, because if you have high value for weights, your loss value will increase. Okay, so you're trying to minimize these. And I think this also covers, like, I think when we were talking about basics of linear algebra, some of you asked like, what is the application of L1 norm, or in fact, like, what is the application of norm? So this is a very interesting application of those norm values. It doesn't have to be L1 norm. You can also use L2 norm and just square those values and try to minimize those. And there are a lot of other variations, but everywhere, like, the motivation is same. You don't want these weight values to be too high, because if you do that, then those weights will actually control what kind of prediction network is going to make. So, and you don't want that. You don't want to control the output of a network by just like some of those weights, right? You want to make use of all the weights to be able to make like a reasonable prediction. The other interesting idea to regularize your network is just use ensemble. Okay, so what does this mean? Because what you're doing is, each time you're training your network, you are initializing your weights randomly. And you know that the loss function you have, it's not convex. So there could be like a lot of different minimas. And if you have different initialization of your networks, like when you do that like multiple times, which means that even if you train the same network multiple times, the final weights is going to be different, because the initial weights was different, right? And if that is so, then what you can do is, at the end, you can, let's say, train 10 different models, and then come up with a way to like fuse those predictions. You can take average, or you can take, okay, the maximum number of predictions when, let's say, 5 of the network are saying it's a cat, then you say, okay, it's a cat. So there are different variations how you do that fusion. But the idea is making use of multiple networks. And again, these are not different networks, same networks. The only difference is the initial weights were different. Okay, so this is, again, it acts as a very good regularizer, and it, in most practical scenarios, mean this is what it's used. So we don't just use single model, we use multiple models. Okay. Now, another interesting thing is, we initialize the weights randomly, and we want the value of the weights to be different. The reason is, if all the weights are actually equal, so what will happen, your network will not train, because you can think about this, like, all the values in your filters are same, right? So if you have 100 different filters, all the filters are going to give you same output, right? So when you compute the gradient at the end, after you have the loss, so the gradient will be same for all the weights, right? Because the initial values were same, the outputs were same, nothing will be different, and the gradient will not change. The gradient will be same for all the weights. And when you make the update, again, the values will be same. So the network will not train at all. Okay, that's just a small point. Okay, so that's what I said. I mean, you don't just train one, you can train multiple models, and just combine like those scores together. That helps you avoid this overfitting, and it also improves the performance. Another interesting aspect is dropout, and this is very interesting. So what you do is, when you're training your network, let's say you have 100,000 different parameters or 100,000 different neurons, you don't utilize all of those at once. You just randomly switch off some of the neurons. Okay, for example, if this is your neural network, these are your neurons, you actually switch off these neurons. And as you pass your input in the feed forward, you will just ignore these. You will only use like the rest of the neurons to make the prediction. Now, what is happening is, if you switch this off, then whatever loss value you have and the backpropagation, this neuron is actually independent of this neuron. It won't rely on this neuron. It will have to improve by itself. Okay, so that's called co-adaptation. And what will happen then, every epoch or every iteration, you change this. So next time what may happen, this is switched off and this is turned on. So again, this neuron will try to learn irrespective of what is the learning of this neuron. And since this is done like stochastically in a random fashion, so these neurons will never co-adapt to each other. Okay, so you can think about this. Let's say you are working on a course project, right? A group project, and you have a group of 10 students. So what may happen is you might have one student in the group or multiple students in the group who are actually relying on other students. So they won't do anything. What they will do is whatever other students are doing, they will just copy it or do something which is based on what other neurons are doing. So essentially, then those students are not learning at all. And at the end, what will happen is whatever outcome you have from that project, so the good students who are actually learning, that will be used. But those students who are just trying to copy the other students, they are kind of useless because you don't need them, right? Even if you don't have those students, your outcome is not going to change. Now, what we are doing is we are shutting off like those students randomly. Then if one student is actually relying on other student, if that student is not present in one of the class, then the student will have to learn. Otherwise, this student can't minimize its loss, right? But it will not produce like good predictions or good outputs. So then it will have to learn. And again, it can try to co-adapt to other students, but again, in some of the other classes, those students will be absent. So that's like a general intuition how this dropout works. And again, this also helps you in like reducing the overfitting issue. Okay, so these units are useful independently, and ideally, like you set this to 0.5, which means that you turn off like 50% of the neurons. And sometimes this is too high. I mean, sometimes you do like 5% or 10%. That again depends upon what kind of architecture you have and what kind of data you have. Okay, so those were like different key aspects which I wanted to discuss. Now let's follow like the training steps. So what you do is you have the problem, you know what problem to solve. So you know like what will be your network's input and what's going to be the output. And depending upon that, you will first define your network. Okay, so you will be the architecture of the network. You will define how many layers you want, how many kernels you want to use, what should be the shape, all those hyperparameters you will define. So that will give you the network. Then you know that what your network is going to predict, and then you know that what kind of ground truth is available. So using those two values, you will define a loss function. Okay. For example, if we are doing classification, you can use binary cross entropy. We discussed that loss function last time. Of course, that's not the only loss function you can use. That's the most like common one, and it usually works pretty well. Then you will randomly initialize the network parameters. For example, if you have CNN layers, you will randomly initialize those kernels. Okay, so those kernels will have some value. Then you will have the training data. And with that training data, the steps which we discussed earlier, you will randomly shuffle it. You want it to be like stochastic. And then you will prepare batches, like the number of samples which you will use to train your network like for one iteration. Okay. So once you have the batch, you will perform that feed forward operation, which is like you will take each sample and you will run it through the network, which means like you are performing all those transformations, all those filtering operations. So it's going from volume to volume all the way until the final prediction. So for each sample, you will predict something. And within a batch, you will do, let's say your batch size is 16, you will do that for all the 16 samples. And so now what will happen, you will have 16 different predictions for the network, and you will have corresponding ground truths as well. So using your loss function, then you will compute the loss value, like how good your network is doing on those samples. Okay, we'll compute the loss. And then the next step is computing the gradients. So you have the loss function, you will compute the partial derivative for that loss function to all the, with respect to all the parameters. So we'll start from the final layer, and you will use the chain rule to move to the initial layers. So for each parameter in the network, then you will have the gradient value. So that's called like a backpropagation, or you can say like gradient computation. So once you have the gradient value, you know that step from gradient descent, right? So we perform that step for each and every parameter in your network. And that's called like updating the network parameters, and that completes your training process for one iteration. Okay, so you repeat for all the batches. That completes one epoch, which means your network has seen all the samples in your training data. And then you keep repeating that to make your network better and better. Okay, so the loss is going to reduce in each epoch. Okay, so that's like the general idea of training. And again, we'll talk about this like in more detail when we talk about the data loader and when we cover the PyTorch tutorial for you, right? So that's the next lecture. Now let's try to understand like what different parameters we just covered, and let's connect that with the AlexNet architecture. Okay, so all these hyperparameters, or you can say like the network design parameters, we already know. We know like the shape of the image, we know like all these kernel sizes, how many kernels we are using. So that was one aspect. Okay, so that gives you the network. Now to be able to train it, what you need is, for example, like what activation. So we are using radio activation in this AlexNet. And then the dropout is 0.5. You know what dropout is. Batch size was 128. Again, these are the parameters which were used by like that first work which started this deep learning revolution. Okay. And of course, these were like determined empirically. And again, it's not that these are the perfect values which you should follow. It will change with like the data set you're using, with the network you're using. But these are some set of hyperparameters which are used by those researchers. Okay, so they used a batch size of 128, which means like in one batch, there will be 128 images when you compute the loss value and compute the gradients and perform the network weight update. Okay, so SGD was used. That's like the algorithm we discussed. Momentum was 0.9. Again, we discussed what momentum means. Learning rate was 0.01. Again, you know what learning rate is. That defines like what will be the step size when you make those gradient updates. And the decay for learning rate was like reduced by 10 manually after like the validation accuracy plateaus. What this means is you observe like the validation loss, or you can say accuracy. And if it's not changing, they were reducing like the learning rate by this amount. So the idea here is, as you go closer to your local optima, you don't want to just keep jumping around that point, right? You want to go to that point. So if that is happening, which is like this accuracy plateaus, right? Your loss will not change, your accuracy will not change. Then you reduce the learning rate. Then you start taking like smaller steps. Okay. So then L2 weight decay was this. This is again the regularization term we discussed. So this is like a value for that.